Guys are in the right class, Cpeg 312. So this is the undergraduate computer organization, but we are combining it with Cpeg 510, which is the graduate version of this class called Computer Architecture. Okay. So even though I'll be teaching it together, you will be graded differently. If you are an undergraduate student, you'll be compared with all the other undergraduate students. The graduate students will be compared with the graduate students, right? So the first, I'll say, maybe first 60 to, okay, so first 60 to 70% is pretty much same material for both. And of course, for the graduate students, it will become more advanced at the end. And then I'll, try to give the undergraduate students a slightly different material. So anyway, our goal in this course is, of course, to be able to design a complete CPU, a complete modern CPU, right? So all of you use computers, laptops on a daily basis. Inside, you already know there's what you call a computer, but it really is the main engine is called CPU, Central Processing Unit. So how do we design it? What goes inside it? What is the exact circuitry? So that's the goal, and the nice thing is, regardless you are in computer science, electrical engineering, computer engineering, once you see, oh, this is how the CPU works, you become better at using computers, you know how, where the inefficiencies are, and how we can do faster processing and so on. Okay, see, as time goes by, the size of the problems keeps increasing. Okay, many years ago, we solved simple things like, for example, to be able to calculate a spreadsheet and so on. Now, with artificial intelligence, with big data, we need huge amount of processing power, right? So, having a very, very powerful, efficient CPU is key to our future technology. So you'll be learning all those things in this course. So it would be a very, very useful, very, very exciting course in the sense that after you're done with it, you'll exactly, every time you press a key on the keyboard, you'll say, oh, this is what it's doing, okay? Okay, so how will we learn all of this? Okay, so what I do is any course I teach, we start with the basics or fundamentals. So all of you, I know, have taken a digital design course sometimes in your undergraduate work. Okay, where hopefully you guys remember, things like this. For example, this is an AND gate, right? And how does it work? Very simple. If both inputs are 1, output is a 1, right? If any of the inputs is a 0, what's the output? 0, right? Okay, then hopefully there are other types of gates. For example, when we put a bubble over here, it's like the opposite of the AND, right? So, for example, if the bubble was not there, AND will produce a 1, but bubble will invert it. So this is what we call an AND gate, correct? And so this will produce a 0. Okay, so we'll be using like AND gates, OR gates. OR gate is, this is how we draw. If any of the inputs is 1, output is 1, right? Very similarly, some of you might remember this, some of you might have forgotten this, but Don't worry, all of you have seen this before, so we'll come to you very quickly. So this is called exclusive OR. And the way it works is if this is 1, this is 0. If they are different, the output is 1. If the inputs are the same, for example, both are 0 or both are 1, then the output is 0. But if the inputs are different, output is 1. Okay? So by combining all of these building blocks, so the gates are the building blocks of any large system, such as a computer. One of the things that you will notice is, as we go along, is you will realize a computer is designed as a large digital system. Okay, so understanding what exactly is a digital system, and of course, when we build a digital system, we use these simple building blocks, these gates. So in our review of fundamentals over here, first thing we will focus is, first few lectures at least, is forget the computer. I'll just review how do we design a digital system, okay? And once you have a good handle on designing a digital system, then, like I said over here, computer is designed as a large digital system. So then we just make it more complex, and pretty soon we'll be able to create first a simple computer, then more advanced, then super advanced computer, and you'll see what's the state of the art in this field, right? Okay, so now anytime we have a digital system, okay, basically there are two types of digital systems, okay? Or first let me go back up a little bit. A digital system has two main parts inside it, okay? What are those parts called? One is called a data path, okay, which interacts with what we call a control, okay? And of course, we have some inputs to our system. Some inputs go to the data path, some go to the control, okay? And we have some outputs from our system. Some outputs come from here, some outputs come from here. Okay, so there are two fundamental building blocks inside any system. System is, think of a system like, you know, for example, of our car. If you take a look at a car is like a system. A system has many parts in it. Okay. For example, if you take a look at a simple car, we have an engine, right, which is one of the main parts in the car. We have wheels, we have chassis, and so on. Okay. Okay, so once we put these parts together in a meaningful way, that's how we create a system, right? So the nice thing about a computer is, or because computer is a large digital system, it really has two main parts. So if we understand how do we create this, how we create this, we can put together a computer, right? So to give you an intuitive idea, what is a data path? What is a control? Even though you might have heard of this before or have done it before. Okay, data path are all the passive parts that we need in a system, in a functioning system. Okay, control is like the brain of the system. So the job of the control is tell these parts how they will work together. Okay, in each and every clock cycle. Okay, for example, a good example of a system, not a digital system, but a system, in my opinion, good example. I gave you one example of a car, but let me give you a better example. A good example is our human body. Okay, see, if you take a look at ourselves, we are built out of many parts, okay, like hands, legs, eyes, brain, ears, nose, and so on, right? So think of this over here like just like I said, legs, arms, nose, eyes, and so on. So these are all the parts that we need, okay? But for example, if I have to go pick up this eraser, right? My brain is the one that tells these parts how to approach it, right? So my brain issues a signal to my legs to start walking, then to the hand to start moving, to grab it and pick it up. So without the brain, we'll be just a useless entity, right? So very similarly in a computer, what you will see is exactly there will be an equivalent of a brain, okay? Exactly there will be an equivalent of all the parts, which we call the data path. And then once we put it together in a meaningful way, such that the brain is able to tell these things what to do, what to compute, where to take the input, feed it where to connect the output to another subsystem, our computer will be ready, okay? So now let's put more detail over here. So as we discussed, we have to learn first how to be able to design a digital system, right? And as we discussed, it has two main paths, two main parts, data path and control. Okay, so data path, as we further discussed, are the building blocks of the system. Okay, control is the brain of the system. Okay, now let's put more detail over here in terms of a digital system. When we create a digital system, these building blocks typically, so let me give you some examples in a digital system of what are these building blocks. The building blocks are buses, registers, counters, multiplexers, decoders, adders, subtractors, multipliers, okay, and so on. Okay, let me put some flip-flops over here. So I'm sure all of you have heard of these things before, and like I said, I'll quickly review these so that you become very efficient in understanding and using these things. So anyway, so this is how we put together some parts, and the job of the brain is to control these, right? Now, let me give you one more piece of information. Okay, see, both of these, so this is the system. Data path is basically, all these parts are digital circuits. Even the control is a digital circuit. Okay, so now let's see what kinds of digital circuits, what's the difference between these two types of digital circuits. So once we create a digital circuit, you will see it has two main categories, combinational and sequential. Okay, what's the difference between a combinational digital circuit and a sequential digital circuit? In a combinational digital circuit, output is a direct function of inputs. Okay, so for example, you'll be given some criteria. You'll be given some inputs. Okay, and you'll be expected to produce some outputs. Okay, and this is our combinational circuit. Okay, for example, let me just give you a simple example of it. What if I gave you some circuit like this? So if you take a look at this circuit, it has 3 inputs. Let's call these A, B, C. Let's call the output Z, right? If I gave you some inputs, for example, suppose I said this is 1, this is 1, this is 0. Okay, so can you tell me what will be the output? So easy way to, as you already know, what's the end of 1 and 1?
1.
1. See, this is called an inverter. So the way inverter works is if you feed it a 0, it produces a 1. Then this is an OR gate. OR of 1 and 1 is 1. So based on input of 1, 1 and 0, what will be the output? 1. So very easy. You can see output directly depends on the inputs. If I change one of the inputs, the output may change, right? That's what we call a combinational circuit, okay? Now, what's the difference between combinational and sequential? So over here, we have one extra feature over here, which we call the state of the system. Okay, so, and I'll explain what state is in a minute. So over here, easy thing to remember is output is a function of inputs as well as state. Think of state like past history or something, okay? So if I draw a picture of it, okay, and by the way, sequential circuits always have memory. So the state, because it's like a history, we have to store it somewhere, okay? So always have memory. Okay, so the general model goes like this. So we'll compare the two together. So we'll have some inputs. Okay, then we will have a further combinational circuit, just like before. Okay, just like the regular combination. But rather than getting the outputs over here, these will basically go to some kind of a memory. Okay. Whatever is stored in the memory, that's what we call the state. Okay? And then further, we'll put one more combinational logic. And then there will be outputs. Okay? So now if I further connect this part over here, okay, so now focus on this last block over here. Okay, just this block over here. What do you see over here? Output is coming from 2 things, right? It's based on 2 things. What are those 2 things? What's this part over here? Inputs. What's the second part over here? What we call the state, right? So that's what we said, output is a function of inputs as well as state, okay? Now, one more thing that we need over here is this state further feeds back over here. So the feedback is also very important over here. This is what, so the state also depends on inputs in the previous state. So another thing to remember is state depends on inputs in previous state. So as you can see, this is a little more complex than a simple combinational circuit. Okay. But once we review some examples of it and you see how to design it, you'll be able to see it's pretty straightforward, because internally you will see there are 2 combinational parts which are designed exactly like a regular combinational circuit. Only extra part is, let's put a memory, let's put some feedback and connect these in a special way so that we can accomplish these 2 things. The concept of a state and the concept of an output depending on the input as well as the state. Okay? So now let's come and clarify the whole thing. Okay? When we build a computer, okay, as we discussed, computer will be designed as a large digital system, right? A digital system will have two main parts, data path and control, okay? Data path will have all these building blocks over here, okay? Some of these building blocks will be combinational circuits. Some of these building blocks will be sequential circuits. As an example, okay, next lecture we'll design an adder, okay? As we design an adder, you will see that adder is an example of a combinational circuit, okay? So we'll identify what inputs we need, what outputs we need, we'll design the circuit, and we'll build an adder. So adder will be one of the parts inside a computer. See, anytime you write a, let's say a C or a Java program, you say int a equal to 5, int b equal to 7, int c equal to a plus b, right? So remember, this has to be translated to some addition in the hardware, okay? So which part will do the addition? The adder will do the addition, okay? So anyway, some of these parts over here, for example, let's pretend we need a sine unit over here, like sines and cosines, right? As you will see, internally, they are more complex than a simple combinational logic. So sometimes these will be designed as sequential circuits. Okay, so anyway, as we start learning how to design a computer, what we'll do is we'll pick these parts first, individually see how do we design these. Okay. So once we have gotten an idea of how these parts are individually designed together, so then we know what parts to put over here. And how do we connect these parts? We'll connect them through what we call buses or multiplexers. So that's how we'll connect all of these parts as an example, right? Okay, so then comes the brain of the system, which is what we call the control. So the job of the brain is now to start deciding which part should do what in a given time instant. And the time is controlled through, you will see what we call a clock. So we'll divide it into, this is what we call the clock cycle. Okay, so every clock cycle, the brain will tell the data path what it should do, what should it add, what should it subtract, and so on. Okay. So even though these parts, some of these will be combinational circuits, some of these will be sequential circuits. Okay, the control, as you will see, is always a sequential circuit. Okay. So anyway, first couple of weeks, I'll review all the basic digital design so that all of you feel comfortable designing any part, being able to control it. Then I'll start out by creating a very simple 8-bit processor. So anyway, this is how our learning will proceed. So first few weeks will be review of combinational and sequential circuit design. Okay, then review of individual components design needed in the data path, so that we know how each and every part is designed, right? and then review a few simple system designs. As I mentioned, a system always has two main parts, data path and a control, right? So I'll give you some examples of how do we make a complete system, right? So, anyway, I'll be going a little bit fast on this part because I assume you guys have seen it before. So it will be basically a quick refresher, okay? The nice thing is, even if I'm going fast, as you can see, the class is being videotaped, okay? So if something you didn't understand, you can always review the tapes. There's also a teaching assistant that will be helping us, who's very good. I'll give you his information soon. And so your goal in the first few weeks is to feel comfortable with the background, right? So then after first few weeks, most likely first 2-3 weeks, okay, then we'll start on designing a computer. Okay, so what I'll do is I'll start by a simple 8 or 16-bit processor. Okay, as you will see, it will have a data path in it. It will have a control in it. It will have simple instructions to be able to add two numbers, store one number from the CPU into a memory, and so on. But anyway, so now this will be designing the data path and control as applied to a real computer, okay? So once we understand how a simple processor can be designed, then we will make it more advanced. So we'll create a 32-bit processor. Okay, so make it more advanced. Okay, then we will go further and make it a high performance. 32-bit processor. Okay, so how do we increase the performance, meaning so that it can compute as quickly as possible in as short amount of a time as possible? So from design point of view, what kind of things we do in hardware to speed up a CPU, so you will see that, right? Then we'll go to supercomputer design. Okay, so the last part of the course I will deal with what is the future of our technology, okay? Not just current state of the art, but 5 years from now, 10 years from now, what kind of computers we'll be using, what are the challenges, so that we can do extremely fast processing, okay? So that's our learning plan over here. Along the way, like I said, every lecture will be videotaped, so if you miss a class, you can always go back and download the video. So let me give you now some course information. Okay, the website for the course. Okay, by the way, I don't use Canvas, so if you try Canvas, you won't get a reply from me because I have my own web server in my office, which is called Kiwi. So your website for the course is kiwi.bridgeport.edu/cpeg. CPE 312 or /CPE 510, no spaces. The graduate students will have a separate website. You guys will go to CPE 510. Undergraduate students will go to CPE 312. Okay. The username is UB student. The password is UB student 2010. Okay. Typically, let's say if we have a lecture on Monday, we typically take a day or 2 days. So by Wednesday, you will have definitely by Wednesday, sometimes by Tuesday. Hopefully you'll have the video recording of the lecture available. Okay. You can always right-click on the link and download it to your computer. If it's taking too long, you can stop by my office, bring a zip drive, and we can just copy it in a minute. Okay. So anyway, all the previous semester's video lectures are already there. Some of the assignments that we did last semester are already there. Of course, every time we teach this course, we make some changes to accommodate for the latest developments in technology. So some of the things will stay the same, some of the things will change, but if you wanted to get ahead, review some of the things, you can all take a look at what was done in the previous semester, right? Okay, you will get about 8 to 10 assignments throughout the course. Okay, again, some of them will be related to some regular digital design. Gradually, they'll be towards the design of the computers. Okay, we have a teaching assistant who is very experienced. His name is Sushant Singh. Okay, I'll put his information and his hours on the website. So if there's any confusion, anything you did not understand, feel free to contact Sushant. Even if the hours are not matching to when you are available, just email him. He's very accommodating. He'll come and meet you and explain any. Once in a while, if I'm not available, he'll come and give a lecture to you as well. Okay. So that we make sure you learn and really understand the design of a computer. Okay. As far as grading is concerned, okay, grading is, I always follow the relative principle, meaning you are competing between yourselves. Okay, the best student will always get an A. Okay, so we have 2 tests, meaning 1 midterm and 1 final. In this course. Okay, so roughly speaking, the weight of the test will be like 35% will be the midterm, 45% will be the final. And then 20% assignments. Okay, so now typically what happens is anytime I teach this course, no matter how much I say, it never works, but I'll try again. Okay. Most of the students copy assignments from each other. One person does it, everybody else copies it. Okay. I'm not going to waste my time seeing who copied and who did the work. Okay. So I will encourage you to do it yourself. However, one way I can make sure is that whoever was doing the assignment gets better grade is when I make the exams, I'll make it such that if you did not do the assignment yourself, you'll be clueless. Okay. So do you want to focus more on the 80% part or get a perfect score over here and then a low score on? So my advice is don't copy the assignments, even if you do half of it right. Okay, remember there's a teaching assistant who will help you, at least he'll even give you half the solution without you doing anything. So half is guaranteed for you. Okay, but if you go to a friend who already knows how to do it and you submit a perfect work, but on the other hand your tests are poor, to me it's a clear indicator you were copying from somebody. Okay, so then I'm not sympathetic. If you deserve a D grade, I'll give you a D grade. Okay, but if you were doing, let's say, 10%, half the assignments over here, but your score is somewhere midway, you know, maybe you got 40% right on the test. To me, at least, you put the effort yourself. So even if you your grade was a C, I'll move it to a B, okay? So please try to do your work yourself. This is how you learn. Only if you're absolutely stuck, go to a friend. But before you go to a friend, go to the teaching assistant so that you understand how things are, how things need to be created or designed, right? Okay, so anyway, at the end, just to give you an idea how I do the grading, let's say the highest student gets an 83, then 81, then 80, then 75, 73, 71, 70, 64, 63, 61, 51, 45, 43, 41, something like this, right? Okay, so the way I grade is the highest student will get an A. Okay, if there are other students that are close to this score, they will also get an A. Okay, then I look for a next break. So now I see there's a bigger gap, so this will go to an A minus, A minus, A minus, A minus, then there's a bigger gap, B plus, B plus, B plus, bigger gap, D, bigger gap, B minus, B minus, B minus, and so on, okay? So anyway, if you wanted to do well in the course, once again, try to pay attention to the lectures, okay? There is a reference book. You don't have to buy a book because the material keeps changing. In my opinion, anytime a textbook comes out, a few months later it's outdated because technology is changing so fast, right? Okay, so I'll be designing everything in front of you on the board. So that it makes sense, it's proper. If there's any advanced material, especially we go to the supercomputers and so on, I'll be giving you some research papers and explaining, and you'll be doing some exciting things at that time. Okay. And last suggestion is, if I'm explaining anything and it did not make sense, don't hesitate to ask. Okay, remember you are here to learn. If you keep quiet, I'll assume you're understanding, I'll just keep moving. So feel free to stop me and say, Professor, explain it again, it doesn't make sense, okay? So this way you'll learn more, the class will be more interactive, more exciting. So anyway, that's the overview of the course. So today I won't give you any real lecture, just an overview. If you have any questions, let me know. Otherwise, the real content will start from next Monday. So, any questions?
Reference book.
What's that? I'll put it on the website. I don't remember off the top of my head. Once you go to over here, you'll see the reference book. Okay, so try to be here on time. Our class time is 9:30 to 10:45. I'll start promptly at 9:30. All right.